Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody watching us from the future. We are in the advanced part of information retrieval. As you might remember, now we are tackling the advanced topics for retrieving documents. I will finish today, hopefully, this probabilistic retrieval part, and we will hopefully have some time to continue with language models. And before that, I will ask you a few questions. Thank you. So that we can check that you've been following. So let me go there. Here is my first question. Which of the following does not always apply? So is it that the sum of the probabilities of all elementary events must be 1? Is it that each elementary event must have a probability of either 0 or 1? The elementary events are the elements of omega, big omega. A probability must always be positive, and probabilities of elementary events must all be equal. So some of these do not always apply. Oh, wow. There's a lot of disagreement in here, but we do have a majority for 2 of them. So the sum of all the probabilities of all elementary events must be 1. That's the definition of a probability measure, right? You need to sum up to 1. It's a normalization of the probability. A probability must always be positive. In classical probability theory, that must be, right? You must have positive probabilities. It turns out that there exists negative probabilities. It's actually a brilliant idea by Richard Feynman, if you've heard of him. And he wrote a wonderful paper about the use of negative probabilities and what they could actually make sense. And in short, he uses negative probabilities a bit in the same way that I, the imaginary number, was invented, right? They realized that you could solve polynomial equations by positing that there is a number I such that the square is -1, and then you calculate, and at the end, there's no more i's, but it solved your problem. So negative probabilities are a bit the same. You use them on the wave to do your calculations, but at the end, they're gone, and you're left with positive probabilities. But that was a parenthesis, because classically, in probability theory, normally, you require that they must be positive. And it shows that there's always geniuses that are going to have all of these brilliant ideas to challenge things that are taken for granted. Then the probabilities of elementary events must all be equal. No, that would be a uniform distribution, but it doesn't have to be. We also have probability distributions that are not uniform. Yes, yes. Ah, yes, absolutely. Yes, you're right. So yes, actually, if that was a quiz, you could make an argument on that and win. Absolutely, because this is true. Must always be positive would technically exclude 0, and the probability can be 0. Yes, you're correct. Thank you very much for this. Yes, absolutely. I had in mind, what I had in mind when I wrote that was negative probabilities, talk about them. But you're absolutely correct. That would win an argument. All right. And the last one, yes, each elementary event must have a probability of 0 and 1. No, that would be very restrictive. That would basically be a probability distribution with a certain event, and nothing else can happen, right? So that surely does not always apply. All right, so very good. And thank you very much for your remark. It's probably my French origins, because when we say positive, negative, it depends on the language, whether you include 0 or not. So there's different conventions across across areas. But in English, positive actually does not include 0. All right. Then I have maybe this. Still on probabilities, to not switch the context too much. Which of the following statements are true? Do not be scared. It's always the same statements with things that change, right? It's just all the possible combinations. So if two events are independent / disjoint, that's the way it changes, then the probability of their intersection / union, depending on the statement you're looking at, is the product / sum of their respective probabilities. And normally there's two of them that should be correct. You just need to find the right combinations in here. So it's about the definition of independence, well, more the characterization of independence and disjoint events. Remember that an event is a subset of omega, right? It's not the elementary one, so an event is a subset. Normally, you should know all that, but it's a good thing to always bring it back to the top of your brain. So let's see if we have a majority. Aha. So I see already one answer very popular here and another one there. I see now some people are changing their minds. Let me close it. So yes, indeed, independent events means that the intersection is the product of the probabilities. So these are independent events. Multiply them. And if events are disjoint, then you can compute the union as the sum, right? It's like, for example, the probability that it's raining and the cat is outside. If it's independent, then it's the product of the probability that it rains times the probability that the cat is outside. But we know that these two are not independent. So disjoint would be if you have a die, for example, and the probability of obtaining an odd number, you would sum 1, 3, and 5, for example, because getting 1, getting 3, and getting 5 are disjoint, right? So you can just sum them. They cannot happen at the same time. All right. And then I had a third one before I continue with my slides. Which one of these ratios did we not define as an evaluation measure, meaning that we did not give it a name? Is it true positives over all returned results, true positives over all relevant documents, true negatives over all non-returned documents, and true negative over all non-relevant documents? The third answer has the majority. So prove that to me. What are the names? So the first one, true positives over all returned results. What is it called? Can all say it at the same time. True positives over all returned results. Or raise your hands if you have the answer. Yes? It's the precision. Yes, absolutely. Very good. Then we have the true positives over the relevant documents. What is it called? Recall, yes, absolutely. It's called recall. And the true negatives over all non-relevant documents. This one is a bit less famous. Anybody? Specificity, yes. And sensitivity is a synonym for recall. Now, it's been a few years that I keep saying this, that we don't have a name for the fourth one. And at some point, I thought, okay, if we don't have a name for the fourth one, we should make one. So I actually thought about it. And I think we could call it crypto-Thesarion. Because you can think of looking at this third metric, it basically looks at what you didn't return and what you could have that has value that you could have returned. So it's in fact, it's like a hidden treasure, right? It's all the documents that you would actually be useful, but yet you didn't return. And so if you look at, for example, Latin roots, then crypto for hidden, thesaurus for treasure, and ion for ratio, so the hidden treasure ratio. So maybe we can call it crypto-Thesarion. But of course, that's not lecture material. It's just that I thought maybe we could actually give it a name. All right, so let's continue then. So we were in probabilistic information retrieval, and I will immediately jump to where we were last time. So I'm going to give you again the context. We look at it from a probabilistic perspective. We have random variables, which you remember are neither random nor variables. They are just deterministic functions. For documents, for queries, and for the relevance. And so I gave you this thought experiment because when you do mathematics, you manipulate formulas, it can be very useful to come down to the underlying structure, right? And when you look at omega, it becomes simple because you just have a set that contains elementary events, and then you have for every elementary event, you have a document, a query, and whether the query, the document is relevant or not for the query. And you just imagine you have septillions of times. And once you have this, then everything makes sense. The probability that a document is a specific document, the probability that a query is a specific query, the probability that the document was relevant, the probability that a specific document is relevant against a specific query, and so on and so on. Once you have this omega space, you can write all of these formulas with random variables and conditional probabilities, right? So this is the approach that we used. This idea of doing that, maybe I can say a bit of history, it started in the 60s. So it was suggested that we could rank the documents in the output of the system by probability of relevance, by decreasing probability of relevance. And that is called the probability ranking principle, PRP, it was called. So probability ranking principle. The context back then was that we only had Boolean retrieval. And so the probability ranking principle was an improvement over the Boolean retrieval that introduced ranking, right? So these were the early days of ranking documents. And so it was invented in the 60s, then in the 70s and 80s, it got improved. And then there's modern systems like Okapi that were created in the 90s and that are still in use today. In fact, we will see why a lot of that is still in use today after we have derived the formula at the end. Then you will see there will be a rabbit out of the hat in what comes out of this. So yes, the probability ranking principle, and that was a fundamental principle. The second principle that I mentioned last week is the binary independence model. It's the idea that the terms in documents occur independently of each other. So this is, in fact, what allowed us to factorize the probability. Here, it's a probability of a document given that it's relevant against a query Q, divided by the same with R equals 0. And what we did is we factorized that into a product over the terms, product over K of the probability that our document contains or doesn't contain term K. And that product here, the product of these D subscript K, is the binary independence model. This is what says we are allowed to factorize this as a product. And of course, that's an assumption. It doesn't have to be, but we assume. And you remember, product of probabilities, that is independence, right? That was the clicker question I asked earlier. So they are independent for each term, and so we just multiply them. So yes, so this is where we are. So we are in the 60s, in the early ages of ranking retrieval. And so now we are going to continue to derive this beautiful formula that you have right here. This is where we stopped. So I would like to insist, because it's very important to understand what's going on. When you look at mathematical formulas, you really have to understand what everything is in that formula, right? So you remember that the uppercase letters are random variables. They are these deterministic functions that assign a document or a query to every one of these elementary events, the elves in Antarctica. While the lowercase letters are mathematical variables, these are actual queries and documents. So D lowercase, for example, could be the latest Dan Brown novel. Q lowercase could be somebody who just types information retrieval in their search engine. That would be Q. And so you really need to really understand the lowercase, uppercase. That is very, very important. And so when I say uppercase D subscript K, I'm going to maybe show because it's easier. So this one, that is a random variable. That is a yes-no random variable. It tells me yes or no, does the document contain term K? For example, K could be information. Lowercase d here, subscript K, tells me it's a 1 or a 0. If it's a 1, then this says K is in the document. If this is 0, then it means it's not in the document, right? And so D lowercase is just a vector for a specific document. It's the vector of Booleans for the 1 for the terms that it contains and 0 for the terms that it doesn't contain. All right? So is everybody with me? Right? Very good. I just wanted to pause on this and make sure that the notation is clear. So now that we know that, and we know that all of these things make sense because of the omega space and the little elves, now we can start manipulating it. So now I did something here. I cut my product into 2 parts. I just put the factors on the left or on the right, depending. And so what I did is that I basically sorted out these lowercase d subscript K. I just took them separately, those that are zeros, those that are 1. So remember, lowercase d is a specific document. So I'm putting on the left all of the terms that are not in the document I'm looking at. We just put them in here, and then I just put a 0 here. And then for the terms K that are in the document that I'm looking at, then I have them here, and that's a 1. So now we got rid of these mathematical variables just because we split it into 2, right? So these are the terms not in the document. These are the terms in the documents. Okay. Now, the next step is we are going to give names to some of the formulas because now it's becoming a bit complicated. So we are going to give them names. So this horrible thing over here, we are going to call it PKQ, right? So you see, it depends on K and Q, right? If you look at here, where are my mathematical variables? I have Q lowercase and K lowercase, right? So these are a specific query and a specific term. So for every query Q and term K, I define PKQ, which is a number. It's the probability that the document contains term K, given that it is relevant against query Q. Everybody with me? Right? So we just give it a name. We just call it PKQ, right? And we call the other one UKQ. And now we can present this in this form, which is a contingency table, based on the condition that I have on the right. Because on the numerator of my fraction, so at the top, I have R equals 1. So I'm looking at the document that is relevant. That is the upper part of my table. And then we have the probability that, given that it's relevant, the probability that term K is in the document, it's present in the document, that is PKQ. And then the probability that it is not present, that is absent, is the complement, right? 1 minus. Here. And then I look at the non-relevant documents. So if the document is not relevant against query Q, then I have a probability UKQ that the term number K is present, and a probability 1 minus UKQ that it is absent, right? So basically what I'm saying here is that I'm making a distinction. I'm looking at the probability that a certain term is present, but I'm distinguishing whether or not the document is relevant. So this is kind of assuming that it might play a role, right? If you look at relevant documents and not relevant documents, they will have different terms that appear in there. Intuitively, you might think the relevant documents are more likely to contain terms that are in your query, right? Or synonyms or that kind of things. And the non-relevant documents, maybe a bit less, they could still contain them, but maybe a bit more random, right? So that makes sense, right? That you have a distinction, and the behavior of the presence and absence of the terms might be different in relevant documents or in non-relevant documents. That's all we are saying here, right? All right, so we call PKQ and UKQ these two probabilities. It's just a number. PKQ is a number for every K and Q, and UKQ is just a number for every K and Q. Now, this is where the simplification starts, because now this is the part where the people back then, and that went on for decades, starting throwing assumptions and ways to simplify. Okay, let's assume this, let's assume that, and then you remove things for the formulas, right? So it's just mathematical cooking when you do that. And so the way it started was this reasoning. If I have a term, K, that is not in my query, so it means QK is 0. That means term K is not in the query Q. So if I assume that my term that I'm looking at is not in the query, then I'm going to conclude that the appearance of the term in the document doesn't depend on whether it's relevant or not. Here's an example. My query is information retrieval. And I'm looking at the term butterfly. Butterfly is not in the query, right? So Q butterfly is 0. Butterfly is not in my query. Do you agree that if I now look at a document and I'm asking, okay, does it contain or not the term butterfly? Do you agree it doesn't matter if the document is relevant or not, because butterfly has nothing to do with information retrieval, right? So butterfly could be in a novel. Butterfly could also be in an information retrieval book as examples in there, but there's no particular reason why butterfly that has nothing to do with information retrieval would behave differently in relevant and non-relevant documents, right? Is that sensible? Right? That makes sense. So we make this simplifying assumption that for the terms that are not in the query, meaning almost every term, right? Because the terms in the query, there's very few of them, so it's almost every term. For most terms, we are going to assume that the two are equal. Wow, that's actually great, because we are dividing one with the other, right? So if we assume they are equal, we can just simplify with one, right? So it's a very powerful simplification here that we have, right? But that's only for the terms that are not in the query, right? So it means that I have here this product over all terms. Imagine a gigantic product with 500,000 factors, right? Gigantic product. But for most of the terms in my products that are not in the query, the factor is just 1, because that's PKQ over UKQ, but that's 1. So for all the terms such that QK is 0, the factor is 1. So it means that I can restrict my product to just the terms in the query. Do you agree? Right? If I do the product, all the terms that are not in the query, it's just 1. It's like times 1, times 1, times 1, times 1, and I'm just removing the times 1. That's what I'm doing. So now I'm restricting the product to just the terms that are in the query. Now it's a very little product now, right? We have very few terms left. These are just the ones that are in our query. Okay. So now let's continue to simplify. This one, I hate to explain because there's no explanation. I try to find one. I'm like, why do we assume that? So this contingency table that we look at whether a term is present or absent in a relevant or irrelevant document, that depends on the query. right? This is why we have the Q as a subscript in there. That might be different depending on the query, right? If you're looking for a query for information retrieval and a query for butterflies in the canton of Uri, then you would assume that this contingency table is going to be different, right? And so here what we simplify is that we say, okay, no, it doesn't depend on the query, right? We assume that this table of present or absent, depending on whether it's relevant or not, doesn't depend on the query. The first time I saw that, I was shocked. Like, how can you assume something like this? Of course, it depends on the query, right? And I looked it up a little bit, trying to figure out why, because in the book, they don't say, in the textbook, they just, in the textbook, they just go ahead and remove Q, but without an explanation, right? So I investigated, and what I found was that it just simplifies the formula. So that's the benefit we get, right? It simplifies the formula. And if we go ahead and do it and build the information retrieval system based on that, it actually works. The evaluation metrics are actually good. That is the reason why we do that. There is no explanation that I can give you that actually makes sense, except if we do that, it simplifies the formula. And if we build the system, it works. So I hope that explanation is good enough for you. That's basically why we do that, right? So it's just computer scientists at work that are trying to simplify things to build a system. So we're going to go ahead and do that. We remove Q from the subscript, meaning that doesn't depend on Q anymore, and we just have PK and UK. So let me remove Q. I'm going to press that button. There you go. It's gone. Okay. So now we just have PK and UK. We assume we can compute them in some way. I'll come back to that later. So now I'm just replacing this PK and QK. Now I did something, I just didn't swap them again. I shouldn't have done that. I swapped the two products, and I understand that might cause confusion. I just realized a bit later. So this one I'm putting on the left, and this one I'm putting on the right. So let's start with this. So this is the product such that for all the terms that are in the query and that are in the document, right? We have DK and QK that are one. So these are the terms in the query and the documents. PK over UK. So I'm putting them here, the terms in the query and in the documents, PK over UK. Now I'm taking the other one that was on the left, I'm putting it on the right now. And what is this? It's 1 minus, right? Because now I'm looking at the probability of not being in the document. I have a 0 here, I have a 1 here, right? And I have a 0 here. So that's the complement, 0 instead of 1, because there's only two values, zeros and ones. So that's 1 minus. Now I have 1 minus PK and 1 minus UK, right? So which is which? So the R equals 1, that is the 1 minus PK, and the R equals 0, that is 1 minus UK, right? So on the documents that are in the query and not in the document, which I put right here, not in the document, in the query, and now I have the complements. Who agrees with this? All I did was replace this horrible formula with PK and 1 minus PK and so on, right? Plus, unpedagogically swapped the two sides, which I shouldn't have done. I apologize for that. All right, so now we have this, and that I kept. It's just the same as before. All right, let's continue. Now, I'm going to do some mathematical hocus pocus. Do you agree that if I have a mathematical formula, I can multiply it and divide it by the same number, right? I can do times 42 divided by 42. That's the same, right? So I'm going to do that. I'm going to multiply and divide by something. Oh, I added a few explanations, which I give already. So these are the terms in the documents, and these are the terms not in the documents, right? All right, so I'm going to divide and multiply with the same thing. So at that point, you don't need to care what it is that we divide and multiply with, because that would always be true. I could multiply it with absolutely anything and then divide it with the same. It's still the same, right? So I can do that. I'm allowed to do that. And you will understand immediately why we specifically divide and multiply with this, because that's actually going to tweak the formula in a good way. So I'm going to multiply and divide with this product of the 1 minus PK over 1 minus UK for the terms that are both in the query and the documents. So I'm going to divide in here, and I'm going to multiply in here, right? Now, here's the easy side. If I multiply this with this, you notice this is the same factor, right? It's the same. It's 1 minus pk over 1 minus uk on the two cases, right? What is different is that we don't do the product over the same terms. Here we have a product over the terms that are in the query and the documents. Here we have a product over the terms that are in the query and not in the documents. Do you agree that if I multiply this with this, that amounts to saying that I have the product of this thing over all the terms in the query, period, whether or not in the documents, right? I'm just doing the union of these two. So now I end up with just the terms in the query, right? Because those that were not in the documents were here, those that were in the documents were here, and I just multiply this. So I have one less filter in here because I just put them together. The other one is more boring because here I have exactly the same product over the same terms, those both in the query and the document. So these are kind of exactly the same support for my product. So I just need to multiply this and this. To divide. This divided by this. And this is what I get, right? I divide, so 1 minus pk is now at the bottom and 1 minus uk is at the top, right? So do you agree I can do that because I just multiplied and divided with the same thing? And what thing did I use? Well, I did it in such a way precisely that here I get rid of d, right? Because now there's no d anymore. But now look what happens. There is no d here, no d here, no d here, no d here, no d here. There is absolutely no d at all right there. Do you remember what we are doing right now? We are ranking the documents. We are doing that for every lowercase d. Do you agree that this here doesn't depend on d? So it's basically a constant. Do you see why now I multiplied and divided? I just wanted to get rid of the d because there was a d right here. I just wanted to get rid of it. So I just neutralized it with this. And this now doesn't depend on d anymore. It is a constant. So since we want to use that to rank the documents, we can just get rid of the constant. And that goes directly into the trash can. Okay? So now we are left with this. So you see we are making progress because the formula is actually getting simpler and simpler and simpler, right? We just had to do this outrageous assumption that we can remove q from the subscript, but we are getting there because we are getting something that is now becoming simple. Plus the product is super small, right? It's the terms that are in the query and in the document. There's very few of them. It's a very small product that we have here. All right. Now we are going to do something because that's a product. But if you remember all the algorithms that I've showed you before for, in particular for the vector space model, you remember the scalar product. The scalar product is a sum of the products of the coordinates. And that's what we called evidence accumulation, right? I was going through the posting list, accumulating the scores, adding. But here we are multiplying. Who knows a magical tool that turns products into sums? Yes? The logarithms. The logarithms turns products into sums. So we are going to apply a logarithm. Do you agree logarithms are a monotonous function, increasing? So if we rank documents, we can take the log. That doesn't change the order of the documents. So let's take the logarithm of this thing. And when we do, bam, it's a sum now. That is awesome because now it starts looking like evidence accumulation, right? Now we need to sum. And what are we summing on? We are iterating over the terms contained in the query and the document. Do you realize that's exactly the evidence accumulation thing, right? When we iterate over the posting list and we add for the queries and documents, for the postings, that is for the documents containing the term. So I love that. This is really getting somewhere here. And so now we even have an interpretation for that because you know that when you divide the probability by 1 minus the probability, that's called the odds, right? I explained last time, right? P divided by 1 minus P, that's the odds of something happening. So we are looking at the sum over the terms that are both in the query and the document of the log of the odds of containing term K in relevant documents minus log of the odds of containing term K in non-relevant documents, right? So I'm basically pushing up relevant documents and pushing down non-relevant documents right here. All right. And remember, pk and uk come from this contingency table. I have them for every term. So I have 500,000 terms. And for each one of these 500,000 terms, I have a value for pk and for uk. Right? I don't know yet how to compute them. We'll figure that out later. But assuming we can, now we have a way to compute a score. It's called the retrieval status value. That is the value that is my score. So if I call that ck, that acts as whatever I do the sum of. And so I basically have defined something that is the sum over all the terms that are in the query in the document of some value ck. Now, do you see the link here? This here basically connects to what we've seen before right here. We just need to walk down the terms in my query and in the document, so looking at the posting list, and I just add that to the bucket, iterating over k. Who sees that? Right? It's incredible, right? So the math was worth it because now we have something that we can implement. We can go ahead and implement that. And because of this insight, you realize that's actually a scalar product, right? You can see that as a scalar product. Scalar product of what? Well, you could imagine, for example, that in the query vector, you have ones where the term is there and zeros when it's not there. And in the document vector, you have ck when the term is here and 0 when it's not there. And if you compute the scalar product of those two vectors, you get exactly that, right? So you can see that as a scalar product again, right? So now we are getting close to even the vector space model, right? It's incredible because that has nothing to do with anything, right? We just started from scratch on probabilistic information retrieval. And now we're ending up with vectors and evidence accumulation. So this is incredible. But there is one thing that we need to do. It's to know the values of pk and uk. Because if we don't have the values, then that's totally unusable. So we need to figure out what values to use for uk and for pk. And so here, you also have a beautiful set of papers over the 60s, 70s, 80s, and 90s about suggestions on what to do to get the values for pk and uk. There are theoretical proposals, people who did that in front of a blackboard. And then there's the practical proposals, people who try to actually evaluate them using real people. Right? And so I'm going to show you a little bit of both, but very, very quickly. So we want to find values for this. Now, let's first use the blackboard. So let's gather a few people in some classroom and have them brainstorm about how to do that. So these people who brainstorm about that might think, let's add totals, right? When you have this, we can add on the rows and on the columns. So let's add a total, so relevant, non-relevant, and then in the third row, I have all documents. So it's the sum, right? Relevant plus non-relevant. And then on the right, the case term present, the case term absent, we have the total. But now I no longer have the probabilities, I have statistics, right? If I did it here, the sum on each row would be 1, right? The sum of the probabilities would be 1. And then the sum wouldn't make any sense on the columns because I'm looking at probabilities, right? But now I'm looking at statistics. You know that probabilities and statistics are connected, right? In fact, we even have courses with that name, right? Wahrscheinlichkeit und Statistik. They belong together. So when you want to evaluate probabilities, you can just gather some statistics, and then you use the ratios that you get from the statistics as estimates. We call that the maximum likelihood estimate, right? So we can use statistics, just look at real data, real world data, and try to derive pk and uk from the statistics with the maximum likelihood estimate. And so if we try to do that, we can try to fill the table with statistics. So let's start with the easy part. So the easy part is the total row right here. Because what are the statistics? So now I'm looking no longer at probabilities, but at statistics. So the number of times that the case term is present in a document is the document frequency, right? The number of documents that contain term k, that is the document frequency of term k. The total number of documents is n, and you agree that the number of documents that do not have term K is the total number of documents minus the number of documents containing the term, right? Because it's complementary. This and this give me this. So this is easy to fill. And then, so the people in a classroom, they don't have real data, so they just need to give names to whatever they don't know. So we give a name small s right here and big S right here. We just, figure it out later, but we give names here. Now, do you agree if I have here small s and the document frequency, here I have the difference, right? Because again, the sum of these two must be this. So this must be the subtraction. And here I have this horrible sum right here that is again this minus this, and this was also obtained from this minus this. So all I did was try to fill the table with these statistics, right? And the insight right here is that we have a document frequency in here that can be helpful. All right, and now I remove the totals, and now I get this, right? So this, assuming I would have some value for uppercase s and lowercase s, that would work, right? Because big N, I know how to evaluate it. I just need to count how many web pages there are on the internet, how many books in the library. And DFK, I can build that by scanning the books, right? Scanning the number of documents. So now we kind of have something that starts looking like a solution with lowercase s and uppercase s that are left to evaluate. But fortunately, we have very smart people who make simplifying assumptions. And so I'll come to that. So now if we have this, right, and I can plug it into my formula, right, the log of the odds minus the log of the odds. By the way, you know that in the same way that logarithms turns product into sums, I can replace the minus with a plus and swap them, right? I just have -1. So to the power of -1, you take the inverse. So that's why I have a plus between the logs. But anyway, if I plug it in here, then I have that CK is this horrible bunch of divisions and multiplications and additions and subtractions. So this thing right here. And then we can use that in order to add the numbers. Now, there is a little something that we do in these cases. Because remember that, at least for dk and n, what we are doing is we are counting from real data. So I might have a library, and I have books, and I look at the data, and so I fill my statistics. Lowercase s, uppercase s, you could imagine that you organize some live experiments with people in the university, and you ask them to stamp documents as relevant, non-relevant, and that gave you the value of small s, big S. Now imagine that I'm looking at a small library. I'm not looking at the whole internet. I'm looking at a small library that has 1,000 books or 10,000 books. And we did all of that based on these 10,000 books and maybe based on 100 people to whom we asked, is it relevant or not? Do you see that this is a very small sample size? Right? If I just do that with 10,000 books and 100 people, the precision I'm going to get here is not great, right? And there is something worse. Is that, let me do it here. I'll come back to the 1/2, which is the solution. So if I try to count my document frequencies and everything on a small sample, what's going to happen is that I'm going to have a lot of zeros where the values are small. For example, I'm looking for a word, let's say, supercalifragilisticexpialidocious, right? Very rare term. It actually appears on the internet. You can look for it. But very rarely. Now, if I'm the small library in a small university, it's likely I will not find that term anywhere. So what document frequency will I have? 0, right, in the library. But on the internet, it's not 0. It might be a small number, but it's there. And so this is a discrepancy that has to do with the small sampling size. And so there is a trick for this when we want to avoid the fact that when I sample, I'm going to get a lot of zeros where in fact what's happening, small zeros where in fact it should have been small values, so I'm far away. And the trick is to smooth things out by just adding a constant everywhere, right? So you run your statistics and then you add 1/2, don't ask me why 1/2, but you add 1/2 everywhere, you smooth it out, and that is going to turn this into this. All you do from here to here is to add this 1/2 everywhere. And do you see that doing that, you're closer to reality, right? So it's basically amounting to saying the terms that I never saw in my library, I'm not going to put 0 in there. I'm still going to lift it a little bit to say, okay, maybe they still appear somewhere, smooth it, and then I get the smoothed statistics. And that's what we are doing here. We are adding this 1/2 everywhere. 1/2 just because it's a way of adding a little bit of something. Then I smoothed it out. So even for the terms that I might not have seen, I still don't have a 0 in there. I still lift the value up a little bit. Who is with me? Right? All right. So that's the explanation of smoothing. Now, I still need the uppercase S and lowercase s, right? And so what can we do with that? Well, here's what people suggested, and I absolutely love that. So first, there are two people, Croft and Harper. They said, okay, in relevant documents, we're just going to assume that the odds are 1. So we're just putting 1/2 and 1/2, and that's it, and we are done, right? And that's great because now I got rid of all the values in there. And for the other one, what can be suggested is to just remove the s, small s, big S. We just assume that it's very close. Remember that when you have a query over the internet, the relevant documents are very few compared to the entire internet, right? When you do a search on the internet, the documents you're looking for are relatively a very small subset of the internet. So that means that the non-relevant documents, that's almost the entire internet, right? So what we are doing here is we are saying, okay, not relevant, we are just approximating it with the total. That was the total row that we had, right? So we are replacing with the document frequency and n minus the document frequency. And so we got rid of uppercase S and smaller case s. How convenient, right? Turns out it works. And that is the break, and I'm going to finish that after the break and go to the language models, right? But you see, simplifying assumptions, they are great, especially when at the end the system actually works. So thank you, and see you in 15 minutes at 17 past.